Hi everyone. In today's lecture, we are going to talk about the basic computer arithmetic which we use in this course. So here, the content that you can find the optional reading from the book Computer Organization and Design, the chapter 3, which covers the arithmetic for the computers, and from the second book that Computer Arithmetic, a quantitative approach, where you can find some the additional readings at the appendix of A, which is instructions and principles part. There you can find. So in this lecture series, we are going to talk about the binary and hexadecimal representation, binary to other representation that we see, then do some basic binary maths, then the two's complement, floating point numbers, and then by getting this knowledge, we try to design a ALU, the hardware design part, right? So the binary and in hexadecimal numbers, before going to talk about that, we talk about the number system in general. In number system, we find in day-to-day life, that is the decimal numbers. So what does decimal numbers represent? Simply, here you can see the example that what does this 5634 represents. So it says that the 5637, sorry, 34 as your decimal part, means as a decimal number. So how it is expanded, that means the every digit in this decimal number is multiplied by its radix, we call. So that is 5 is represented with the 10 to the powers will be written from 0, 1, 2, 3, and so it goes. So it will be represented as 5 multiplied with 10 to the power of 3. So that is 0, 1, 2, and 3 here. So it becomes 3. Then that item is added with the next item, that is 6 multiplied with 2 to the power of 10, that is equal to your 600, and your 3 multiplied with 10 to the power of 1, that is equal to 30. And next item is your last digit, that is 4 multiplied with 10 to the power of 10 is equal to 4, and by adding all these it will give our number. So from this, what we can observe in this number system, what is this 10 here, where every time we are the multiplying. So this is called the radix part of your number system, radix part. Okay. And what is the type of the number system, which we call it as your, if it is following the radix as your 10, we call it as your decimal. And what are the digits for this decimal numbers means it use 10 digits. It use 10 digits that starts with 0 and ends with the 9. So total, if you find this total number is 10. So we call this decimal numbers. So the combination of 0 to 9, every number will be represent. So what are the digits for radix or numbers? So the digits of your R, radix number can be written as your 0, 1, 2, and so up to R minus 1. If R is 10, that means up to 9. If R is some other numbers, it can use that. So then the basic understanding of this decimal, as just we saw, there will be 10 digits will be used, starts with 0 and ends with your 9. The combination of all these will represent the decimal number. But how many times does a decimal number represent means how many the digits are there in this decimal number, that many items will be calculated. So for 1, 2, 3, 4, that means there will be 4 items will be there. So what about the fraction part means when it is a positive number and when it is a integer part, when it is an integer part, so then every digit is multiplied with 10 to the power something. But when it becomes to your fraction part, suppose that we call the decimal or dotted decimal part, then after that it use the negative power of your 10. so that the first 5 digits, they will be multiplied with 10 to the power of positive numbers, and the fractional part will be multiplied with the 10 to the power of minus part, and the sum of all the items will give this number. And formally we just represent the decimal number like this, the this integer part and the fractional part, and at the base we give 10. So similarly, to understanding the octal numbers, octal means it is 8. So if you take the base 8, or if r is equal to 8, then the maximum digits which are used in this octal number is your r minus 1, that is your 7. So it starts from 0 and ends with 7. So the combination of your 0, 1, 2, 3, 4, 5, 6, and 7 will represent. That means if I have the number 286, do I consider this is as the octal number or not? Means by just observing this number, we can say this is not an octal number. Why? It is having a number 8 here, which doesn't exist in the octal form. So the number representation, or how many items does an octal number represents, means again the same procedure. How many digits are there? They are multiplied with the 8, so that it will be converted into your binary form. So what about fraction? Same procedure we use. The integer part will be multiplied with 8 to the power of positive numbers, and the fractional part will represent with 8 to the power of your negative numbers. So the octal numbers don't use the digits 8 and 9. As said, if I have the number, suppose 151896, this we cannot give it as your the octal form. This is wrong. If it is having, suppose, 1 2 3 4 5 6 7, and if I write it as octal, it will be acceptable, right? Similarly comes to the binary form. So binary means it use the 2 bits. So if r is equal to 2, it gives that r minus 1 is equal to 1. That use the binary form of this one. It use only 0 to 1 maximum. Either 0 or 1 bits will be used, or digits will be used. So how many items will be there? Means generally the binary form is written like this, like combination of 1 and 0 and 1, and you can write it as your binary. If I have the number that 1051, suppose, and if I say that this is binary, it will be wrong, because it's having a digit 5. So how it can be written in terms of items means, again, the 0, 1, 2, 3 digits are there. So it starts multiplying with the every digit multiplied with 2 base, and to the power of their position in the binary form will give you the number of items that depends upon number of digits in the binary number. So what about fraction means? The same procedure. We use the negative numbers with the 2 to the power of minus 1 format. So the group of with this binary forms, we can say that the group of 8 bits are called as your bytes. That is represented in this form, that 11001001 as binary, or it can be written as 000 or 000 as your byte. So we call this as 1 byte. And if it is divided into some parts, then like 4 bits, we call it as your nibbles. So then why we use these binary numbers? That means in our the computer architecture, the processor means the processors means they are simply the transistors. The transistors means they are simply formed with the gates. So the gates will use, they can use the inputs in terms of the power. power signals are electric values, we say. So these electric values can be represented in terms of zeros and ones. So that's the reason the binary representation is used. And here it is possible to tolerate the noise with this binary one, and it is easy to transmit the data from one the gate to another gate in your integrated circuits. And it is easy to build the binary circuits, and those combination of the gates will give your circuits, and those circuits will give you the processor for the evaluation. So if there is zero means there is a electric value, zero means it is power off, and one means it is power on, or we can simply say that charged off and charged on. So then we need to, always need to understand the conversion between the number bases. Conversion between the number bases. If any number is there in decimal, that should be converted into your binary. You should understand how the conversion process will take. And then if the number is in binary, that can be converted into a decimal. And similar wise, binary to your octal or binary to your hexadecimal. So decimal, the base is 10. For binary, the base is 2. For octal, the base is 8. The the hexadecimal, the base is 16. So let us see this conversion process in one by one. But the general base conversion for this, in that the number representation given for any of the number representation, it may be your decimal, it may be your decimal, it may be your binary, it may be your octal, it may be your hexadecimal. The general equation, or it follows that for a given number with radix r, this r may be your 10, 2, 8, or your 16. So that is decimal, binary, octal, and your hexadecimal with the of any integer portion. So that is written as your the every digit in that written as your a n minus 1. It goes on up to a naught, I just said. So suppose if I have the number 98967, so it can be written as a. So there are three digits are there here, so we can write a minus, sorry, n minus, here is 3, so we can write 0, 1, and 2. So this 2 is n minus 1, then n minus 2, and this process goes up to your 0. Similarly, for fractional part, if you have any number like 1, 2, 3 dot 4, 5, 6, for this fractional part, the digits will be written as your the from first one it is written a minus 1, a minus 2, and so on, so up to the last digit, suppose a minus 1. So overall the equation for representing the numbers as the combination of your integer part and your fractional part, you can write it as a n minus 1, a n minus 2, a n minus 3, and it reach to the first last digit of your integer part. Then the dotted decimal comes, or the dot point comes, and the fractional part starts from here. So this the summarized one, the value of this can be written as your the number with any radix can be written as your the summation of I is equal to 0 to I is equal to a minus 1, and the integer part of your digit or integer portion of your the number, and its radix to the power of its what you call the integer portion, and the fractional one will be added in the part of your the minus 1. J is equal to minus 1 to your j is equal to minus m portion. So as we just see that there are the common occurring bases are your binary, your octal, your decimal, and hexadecimal. For binary, we use the digits 0 and 1. For octal, as we said, 0 to 7. For decimal, your 0 to 9, and for hexadecimal up to 0 to 9 will be used. From 10th portion onwards, the capital letters will be used: capital A, capital B, capital C, capital D, capital E, and capital F. So now see the converting binary to decimal and decimal to binary, and from there how any number can be easily convert from one base to another base. So to convert a decimal, use the decimal arithmetic to sum the weighted powers of two factors. That is your integer portion as well as your fractional portion. Suppose converting a binary number, converting a binary number 11010 to any the equivalent decimal number, and that will be multiplied as the first bit multiplied as the total number of bits here is 1 2 3 4 5. So it will get your the n minus 1, that is your 5 minus 1 is equal to 4. So the bit starts that the first bit multiplied with the 2 to the power of 4, second bit multiplied with your 2 to the power of 3, and third bit multiplied with your 2 to the power of 2, and one into the next bit is multiplied with 2 to the power of 1, and it is equal to your 26. So we write this n10 is equal to 26, or it can also be written as your decimal part like this. So next one is, if we have this decimal number, how to convert into the binary. So there are, as we said, if it is a fractional, if it is a integer part, then integer part can be simply, repeatedly divide that number by the radix you want to convert to, and save the reminders. So the new radix digits or the reminders in reverse order of your computation, reverse order of your computation. Okay. And if the new radix is suppose greater than 10, that means if it is 16, then convert all the reminders which are greater than 10 to the digits a, b, c, d, e, and the f part. So similarly, for fractional part, it is repeatedly multiply the fraction by the radix, multiply in the integer part, it will be divide. In the fractional part, it will multiply the fraction by the radix and save the integer digits as the result. So the new radix fraction digits are the integer numbers computed in the same order, not in the reverse order. Okay. So this, let us see the example. Suppose if I have the decimal number, the decimal number which is having 46.6875 base 10. If you want to convert this one, as per the first portion, it says they convert the integer part. So you can simply divide the integer portion of your number, that is your 46, divided by your 2. So it will give 23, and whatever the remainder is, that remainder is 0. Right? So similarly, whatever the number is there, that 23 will be again divided with your uh, the number will be divided, and the remainder is 1 here. Then you can divide this 11 with 5, the remainder is 1. Then divide this 5, so 2 to the 4, remainder is 1. And then divide this with 2, 1's 2, and the remainder is, that you can find the 0. So overall, it will going to write this in a reverse order, in a reverse order, in a reverse order. So that gives you the 1011110. So what about this base part? To convert this decimal into your binary means multiply this fraction, this 0 dot your 6875 is multiplied with the radix. And whatever result comes from here, from that result, consider only the integer portion. Consider the integer portion. So here this 6875 multiplied by 2, so that gives 1 dot your 3750. From there the integer portion is 1, 1 will be considered. Next, this number multiplied by 2, this fractional number is multiplied by your 2, so that gives 0.7500. So from there integer portion part is 0. Then this number multiplied, this fraction multiplied by 2, so it gives 1 dot 500. So here the integer portion is 1 is come. So then this 5000.5000 will be multiplied with 2, so that gives 1.00, and this 1.00 multiplied means it gives 0, right? So then this part will be written in order only from top to bottom. Here it is from bottom to top. So then it can be written as dot, your dot 1011, that is base parts. Then the combination of the integer part is 101110 dot, your fractional part is your 1011. So that is the binary form, which is equivalent to your 46 dot 6875 into your base. So now converting the among octal to your hexadecimal and your binary. So octal to your hexadecimal to your binary, the procedure is restate the octal as a 3, because octal means 8. 8 can be written as 2 to the power of 3. So 3 bits are enough to represent. So whatever the binary forms that you will get 1011101111, suppose for any number, then divide all those numbers into 3 bits, into 3 bits, and write their equivalent decimal. So that will give you the octal form. So as 3 are 4 binary digits for your hexadecimal, for hexadecimal means it is 16, that can be written as 2 to the power of 4. So 4 bits for your hexadecimal, and 8 can be written as 2 to the power of 3. So 3 bits for your octal part. And so that can be written as starting the radix point and going both the ways. So binary to octal or binary to your hexadecimal, group the binary digits into 3 or 4 bits. 3 means for your octal, 4 bits means for your hexadecimal bit groups, and starting at the radix point, the rightmost bit position, and going both ways and padding with zeros as needed in the fractional part. So converting each group of 3 or 4 bits to an octal or hexadecimal digit can give you, one ways from converting from binary to your octal, or octal binary to your hexa, or hexa to your octa. So any combination can be possible this way. So let us see. We have a number, octal number, which is given, suppose 635.177. So is it octal or not, means we can say it is octal. Why? Because all these numbers, it may be in the integer portion or in the fractional part, it used the digits from 0 to 7 only. 0 to 7 only. So then try to convert this octal into the binary form. So as octal says that 2 to the power of 3 is equal to 8. So every digit can be represented with 3 number. So 6 can be written as your 110, 3 can be written as your 011, 5 can be written as your 105. That is the from decimal part to your what you call the binary form by following the octal. For 1 can be written as your 001, and your 7 can be written as 1 1 and 7 can be written as 1 1. That is binary form of, so conversion from octal to binary. Now convert this binary into your hexadecimal. So in hexadecimal, as we are saying that it requires 2 to the power of 4 is equal to 6, so it requires 4 bits. It requires 4 bits. So then you start adding 4 bits, 1 2 3 and 4 bits, then the 1 2 3 4 bits, and the last bit is this one. But only thing is, when you converting into hexadecimal, from here you will get 1 2 3 4 bits, 1 2 3 4 bits, one bit is there, remaining bits, remaining 3 bits will be filled with your zeros for regrouping. So then it gives the value as, it is 1, this value is your 9, this value is your, D. So that is your 30 part, and then it gives 3. This means your 15. That gives your, the F part, and this portion is your 8. So this is a simple way of converting, some simple way of converting from octal to binary, binary to hexadecimal, or vice versa. Suppose if the number is in the hexadecimal, then you can write its binary. You can write its binary form, and then you can convert it into, so any number, it may be in your octa or hexa, or your, the decimal. Convert them into binary first, and after converting into binary, you just try to grouping the numbers. So by grouping number, you can automatically convert from octal to hexa, hexa to binary, binary to, the hexa, or binary to octa. So then comes to some simple binary arithmetic. Some simple binary arithmetic. Here we talk about the single bit addition with carry, a multiple bit addition, single bit subtraction with borrow, and the multiple bit subtraction, and the simple multiplication that we try to find in these. So what is single bit addition with carry? That means, as we know, the binary numbers represent zeros and one. Single bit means adding 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is equal to 1, 0. So we call this bit as your carry bit. So with carry. Or we can write 0 and 1 is your 1, or 0 or 0 is 0, your 1 0 is 1, your 1 1 is 1 0. So this portion we call your carry bit, right? Similarly, for the multiple bit addition, you can see in the multiple bit, suppose if we have two binary numbers, so this is, and adding this one. So by adding the single bits, as said, 1 1 is your 1 0, 1 1 adding is your 1 0. So 1 become here carry, and 0 is here. Then 1 0 is 1, and 1 1 is your 1 0. So 0 here, 1 is carry. Then 1 1 is your 1 0, 1 0, and that is 2, and 2 and 1 is 3. That means your, 3 is your 1 1. So 1 will be here, and 1 is carry. So 1 and 1, 1 0 and 0. So that is 2. So it is 1 0, 0 is here, 1 will be carry. Then 1 1 1 is your 3. So that is 1 is here and 1 is carry. 1 and 1 is 1 0, 0 is here, carry is here, and then here nothing is there. So this is the addition of the multiple bits, or multiple bit binary addition. Then comes to your binary subtraction. So this is a little bit tricky. So in binary subtraction, or we can also call it as your the borrows in place of your carries. In addition, we find carries. in subtraction we use the borrows. So now see, if 1 minus 1 is 0, in single bit it says 1 minus 1 is 0. Your 1 minus 0 is your 1. So same procedure here. 1 minus 1 is 0, and here 0 minus 1, 0 minus 1, that means it is not possible. So it will try to borrow 1 from this number. It will borrow 1 from this number. That means 1 0 0. Let me just rewrite this: 1 0 0 1 1 0 1. From that number you are trying to subtract 1 0 uh, 1 1 1. Then 1 minus 1 is 0, but 0 minus 1 is not possible. So take the borrow here. When you take the borrow, then it becomes this 0, and this 1 becomes your 1 0. So here, when this 1 is borrowed, it becomes 0 here. This becomes 0. This becomes 0. Right? So this 1 0 means its value is 2. So 2 minus your 1, it is 1. 2 minus 1 is 1. So now here 0 minus 1 again not possible. So it borrow. When it borrows, then it become 1 0. That means it become 2, and this portion become your 0 part. So 2 minus 1 is 1. So then here 0, here is 0, result is 0. So 0 minus 1, 0 minus 1, not possible. Take the 0. So that is again 0 0, not possible. Take another 1. So it become 1 0. From there, when it's get, then this becomes 0. It become 1 0. From here it borrows 1. So it become 1 0. So that is 2 here. It becomes 0 here. Okay, this is covered. So 2 minus 1 is 1, and here is 0. It is 0. So that is how the values are borrowed, and finally you will get the result as your 1 1 0 1 1. So this is the subtraction of your two numbers. So then the multiplication, in the multiplication, in the binary multiplication is same as your digital, I mean the decimal multiplication, except that the each multiplication operations are much simpler here. So you can see this number, binary number is multiplied with this number. So then you can multiply 0 multiplied with 1, 0 multiplied with 1. So 0 into 1 is 0, 0 into 1 is 0, 0 into 1 is 0, 0 into 1 is 0. So it is the bitwise operation. Then the second bit multiplied from the second position. So 1 into 1 is 1, 1 into 1 is 1. So the same number will becomes, that is 1 0 1 1 1. Then zeros, all zeros comes. Then another number multiplied with 1, the entire number comes. So then you can do the simple addition, binary addition. So 0, here is 1, here is 1, here is 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1 0. So 0 here, and carry will be here. Okay, then 1 plus 0 is 0, 0 plus 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 1 0, 0 here carries here, 1 plus 1 is 2, 2 plus 0 is 2, 2 plus 1 is 3, that is 1 here and 1 here. So result 1 plus 0 is 1, 1 plus 0 is 1, and it gives the result 1, and finally last one is 1. So this is the binary, simple binary multiplication. Simple binary multiplication. So then the most thing is, now we just covered what is this, the number representation of your decimal, then your the hexadecimal, sorry, your binary, then octal, then your decimal, then your hexadecimal. Then we are focused on these binary addition, subtraction, and multiplication. But in the hardware execution part, it uses the positive signed numbers and unsigned numbers. Up to now, we just discussed the unsigned numbers. So if there are signed numbers, then it requires the some complement encoding procedure. So that we call the two's complement. Let us see what is this two's complement. Since we only have zeros and ones, so the numbers inside your computers will have only zeros and ones. We call them as your charged or uncharged. Charged means one, and the uncharged means charged means one, and uncharged means your zero transistors in our computer. So all computers are represented in binary only. So for unsigned numbers, remember, for unsigned numbers and the positive integers, unsigned and positive integers. Unsigned means simply if you write 5 or 5.5 or 6 or 6.6 like that. So we are not mentioning any sign here. So they are represented with bits corresponding to their binary representation, corresponding to their binary representation. Suppose 5 is there, I'm not using any plus or minus here, I'm just writing only 5. So the 5's binary value is 101. So this is a simple signed representation of an integer, positive integer. But what about the negative integers? Negative integers means we may write -5, -6, -7. So this is, we call this signed one, signed representation. So they are represented using a format slightly different from the absolute values, as there are no negative sign in transistors. Transistors can only understand 0, 1 and zeros. So for that, this format, we call it as your two's complement. To represent negative numbers, two's complements will be used for encoding purpose. So to represent the signed numbers for plus and minus, we can write these signed numbers plus and minus used for decimal numbers as your 25. This can also be written as your plus 25 and minus 16, etc. For example. So there are three types of signed binary number representation. There are three types. We call them as your signed magnitude, one's complement, and two's complement. So what are the types of signed binary number representation? Mean there are three types. One is your signed magnitude, one's complement, and two's complement. So let us see in the first one, in signed magnitude. In each case, the leftmost bit indicates the sign. If it is positive, represented with 0. If it is negative, represented with 1. So suppose if I have the 8-bit register, for this 8-bit register, if it is supposed to store this 12 of your decimal number, then that decimal number converted into your binary form to represent this signed magnitude as the value of your binary 12 is equal to your 1100 in the binary, right? So to represent in the 8 bits, you need to add the other 4 bits here, 000 and 1100. So what is there in this 8 bits? The leftmost bits are the leftmost bit is represent with the 0, that we call the sign bit, and rest of the bits are called your magnitude. Suppose if I write this with only suppose 10110, but to represent this positive value, I should add one more bit. So to represent the negative number in the signed magnitude, the last bit will be used with your sign bit as your 1 to represent the negative, and remaining bits will be used for your magnitude. So this is in the signed magnitude, right? But comes to your ones complement. In the ones complement, another way of representation, ones complement representation of your signed binary representation, the ones complement of binary number involves inverting all the bits, inverting all the bits. Suppose if I have the number called your 00110011, the binary number, okay, to convert this or find its the ones complement, that means simply you can, 00110011, to convert this into ones complement representation, convert all the bits into, or invert these bits, that is 1 bit is 0 become 1, 0 become 1, 1 become 0, 1 become 0, this 0 become 1, this 0 become 1, this 1 become your 0 0. So that is inverting one, right? So if you see another number, suppose 10101010, it becomes 01010. So here, what is need to remember in one's complement means how many bits are there in the number. So here in this example, we are having the number of bits is equal to 8, and the given number is 0011. So that is represented as your n. So then, for an n-bit integer number, or for an n-bit number, capital N, the ones complement is a formula that 2 to the power of n minus 1, 2 to the power of n minus 1, and from there you remove, they do the subtraction of your given number. So that is ones complement. So in this example, it is 2 to the power of 8 minus 1 minus the given number, that gives this result. So to find the negative of one's complement, to find the negative of one's complement number, negative of one's complement number, take the one's complement. Take the one's complement. That means here you can see the one's complement representation is of a positive number is like your signed magnitude. Signed magnitude. So that is given as your 0. For suppose for this decimal number, the binary form is your 1100. So for signed, one's complement is the same number only, the same number only. Okay, so as it says, yeah, so same number only. But to make this negative form, this sign bit will be 1, and remaining bits will be inverted. Remaining bit will be inverted if it is a negative number. That is, all zeros becomes your ones, ones becomes your zeros, zeros becomes your ones. So that is the representation of ones complement or the negative number. Find the negative of ones complement number in this way. So then comes to the third representation is two's complement representation. Two's complement representation. So the two's complement of a binary number that involves inverting all bits and add 1 to it. So that becomes your two's complement. Suppose if you have the binary number 00110011, so then the two's complement of this one is convert this, inverting all these bits into the form that is 11001100, and then add another one to this, so that will give your 11001110. Suppose if you have the number this 10010101010, so it inverts 01, convert all this 01010101, and add one number to this one, so it will give the 0101011110. When you add this one with one, it will give that 01010101 and add one. So that gives 1 with 1 is 0, add 1. So 1 plus 0 is 0. I mean the 1 here, then this 1 and remaining it comes as 0, 1 zeros. So to find the negative of the negative number, to find the negative of 2's complement number, you take the 2's complement. So the signed number, assigned magnitude for the given 12 number is this. So its negative, the last bit represents negative with 1. Remaining bits are inverted and add plus 1. So that is all zeros becomes your ones, all the ones becomes your 0 ones, and then add plus 1. So that will give you this result. That is minus negative. So to do this two's complement, there are two algorithms or two steps that can be used. One is simply complement each bit and then add 1 to the result. So as we just did the example, so finding two's complement of this number, you just do the ones complement for this, for unsigned one, ones complement, then that becomes your 10011, that is equivalent to this number. And to write it's the negative one or two's complement of this number, just add 1. So that will give the two's complement of this number. Another simple way to do is this, starting with the least significant bit, that is one. Suppose consider this number, the the given number here is 011000101. Then says starting with the least significant bit from here in this direction. Okay, copy all of the bits up to and include the first one bit, and then complement the remaining bits. So by going this way, 011000101, going in this direction, the first bit is 1. So that can be written as 1, and all the remaining bits will be complemented. So 0 becomes 1, 1 becomes 0, 0 become 1, 0 become 1, 1 becomes 0, 1 becomes 0, 0 become 1. So that is the two's complement of any given number. So either you can follow this way by just doing the ones complement and add 1, or simply scanning the bit from left to right and find the bits. Suppose if you want to find the two's complement of this number, suppose for example, in the example, we can scan from left to right until we find the first one. So first bit is 0, you write as it is. So here is 1, so you write as it is. After that you complement all the bits. That is 0 becomes 1, 1 becomes 0, 1 becomes 0, your 1 0 0 become 1 1, and 0 become 1. So that is the complement. So this is another way of doing the two's complement. So then comes to the ones complement addition. Ones complement addition. So using ones complement number, adding numbers is very easy here. So for example, suppose we need to add two binary numbers. So let us compute the decimal value is here. So 12 and 1 is there. So how can you write? How can you add this ones complement? Means ones complement, they simply write these two are positive numbers. So their binary representation is simply the ones complement. If it is negative, that means that will be added. We'll check that. So these two numbers we can write that the binary value of 12 is, the binary value of 12 is 1100, and it is a positive number, the sign number, so you can write plus. So that gives the signed representation, one's complement signed representation. Similarly for 1, that is binary equivalent is 0001, and plus can be written this. So plus will be replaced with your 0, so that becomes one's complement. Then add these two binary numbers in step 1. So when we are doing ones complement addition, the important point here is it is simply adding the doing this binary numbers. But if you find the carry bit, that carry bit will also be added to the result, so that then it gives the final result. So here 0, 1 is your 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0. Okay. And if it is having any 0 carry, suppose this will be added. Suppose if carry comes, suppose 1, that will also be added. So add carry to the lower order bit in the ones complement addition. Similarly, ones complement subtraction. In the subtraction, the thing is, uh, it do the same operation for plus 12 number. The binary form is 110. So it is positive number, sign number. So sign representation is represented with ones complement as its binary equivalent only by adding 0 here. For minus 1, the minus symbol, take it out, so it becomes minus your one binary representation of this. So minus can be represented with the 1. And to represent this, remember, you need to do the ones complement, means you can the invert all the bits. So 0 become 1, 0 become 1, 0 become 1, 1 becomes 0, and this minus represented with 1 bit, that is the negative number ones representation. So then you can simply add them. You can simply add them. So that is, take ones complement of second operand, that is negative number operand, and add a binary number. Then add those two numbers, that will give you some results. So here in this addition, we got one carry. So that carry bit will be added to this result. So that will give the final result. That will give the final result. So this is ones complement subtraction. Subtraction. For subtraction, remember, it will take the separate the minus, this minus 1 is written as minus 1 in digits. So then it is written into the binary form of your 1 is your 001. Then you are doing the complement or inverse of all these digits and adding this minus at the leftmost bit. So then comes to 2's complement. In 2's complement addition, the only thing is, in 1's complement, we add this carry to the result and then it gives final result. But in 2's complement, the carries are ignored. The carries are ignored. Okay. So in this example, if you see, if you are adding this, this will be ignored. And if you do this example, suppose for subtraction, 2 subtraction, it will get this carry, that will be ignored. So remaining bits will be considered for final result. In the final result, if you do 12 minus 1, it is 11, that is positive. So the last bit is 0, so that is the positive number, it says. Right? So then, see another example. Suppose 13 minus 5, the 2's complement of this. If 13 minus 5, so you can write positive 13 as its binary representation only. So all the positive numbers in terms of signed magnitude or 1's complement or 2's complement, that is equal to that number's binary representation. But when it becomes the negative, its absolute value is something changed. How? So this, you can see the binary value of this 5 is 0101. Then you will complement this as your 1010 and add this minus 1 here. So this is the minus 5, absolute minus 5 value, minus 5 value. Then add this to the positive number, sign number. Then you will get some, the carry. So that carry will be ignored. So when you are doing 13 minus 5, it is your, the 8. So that is the 8 one, and the sign bit is 0, that is positive value, right? So then a simple 3-bit 2's complement encoding. A 3-bit 2's complement encoding. In 3-bit, if 3 bits are there, so first bit is your sign bit, remaining bits are your the number, the number part. So for positive numbers, you can see that is equal to their binary representation. So one can be written as your 001. So 0 is your positive. 2 can be written as 10, but 0 is your positive. 3 can be written as 11 and encoded with 0 for your positive. But whereas your 4, so how it can be written? 4 minus 4 means minus, your 4 can be written as your, the 3 digits part. So that if you follow the formula of this negative, so you can see this 2 to the power of n minus 1 and your minus n plus 1. If you follow that one also, you will see this the number is, you can write 100 minus, so then you do the complement of this one, 011, and do the 2's complement of this one is, you need to add 1 to this, so it will give the result as your 0, and 0 here is 1, so that is the 2's representation of this part. Similarly, your 3 can be written as your with 3 bits you are using, means 2 to the power of 8 minus 1, sorry, 2 to the power of 3 minus 1, that is your 8 minus 1, that is your 7, 7 minus 3 is your the 4, and that representation, it gives the complement bit. So in generalizing two's complement encoding, two's complement encoding, in two's complement encoding with n bits. So this n may be your 3 bits, 4 bits, 5 bits, 8 bits, that depends. So for any positive number, it is encoded with its binary representation only, as we saw in signed magnitude, one's complement, two's complement. For any positive number, it is equal to their binary representation. But for negative numbers, it is encoded with the binary representation of its complement, binary representation of its complement. So that is, in the previous case, minus, the 4, so we use 3 digits, so 2 to the power of 3 minus your 4, so that is equal to your 7 minus 4 is equal to 3, that can be represented in terms of your 011, that is 0, the 11 minus 3 minus 4, that you can find there. So note, for 2's complement encoding, the highest bit for a negative number is always 1. The highest number is always 1. So this is the generalized 2's complement. And with this, I would like to stop this session here. If you find